Hello.
Excuse me.
Hello. Yeah.
I got a bit of a sore throat.
Oh yeah.
Tis that season.
Yeah.
My daughter's been home for 2 days.
Oh. Yeah. So what's going on with you?
Maybe I need some more light.
Yeah. Here we go.
More presentable here. Yeah, I this week. Let's see. Well, it was JPM Healthcare this week, which is a huge industry conference. The joke is that no one you know has ever attended JPM Healthcare because JPM Healthcare is a invite-only meeting that is for bigwigs and people with real money.
Yeah.
So there's a bunch of euphemisms for the conference ecosystem that is not actually JPM Healthcare. But a bunch of people do events at the same time as JPM Healthcare. And those were great.
Good.
So it was we did a demo day with Kernel, which is this near infrared imaging helmet. Although they make dev kits, so you don't actually have to use the helmet. But that's their really interesting device to track blood oxygenation. So you can use it as kind of a less demanding MRI system. It only sees about a centimeter deep into the skull, so you can only kind of capture what's happening on the top of the head.
Yeah.
And so the two things. One, because of the helmet itself, it's like where the sensors are, you're really capturing only the top of the head. And then two, your depth is limited by the photon transport and how many of the very, very few photons go into the head and then come back out. But those are the ones that you detect.
Yeah.
So deeper is much, much less likely that the photons that go deep will come back out, or certainly come back out to where your sensors are. So it has some limitations in that regard. But you don't have to have a 2-ton super cooled magnet system. So it is kind of portable.
Yeah.
And then just another nice meeting on Thursday with companies talking to two startup founders. One was a PhD from Stanford, from the lab that one of the co-founders from Neuralink, and the other a PhD from Oxford, who went through the same lab that I did, with Tim Barron's doing animal electrophysiology, although now she's doing a very consumer-facing company. Anyway, that was great too. Really nice. we now have, there's a bunch of UIUC students here.
Oh, yeah?
Yeah. So I'll meet up with them today. So they're all with Neurotech at UIUC.
Okay.
One is the kind of like partnerships manager.
Okay.
Excuse me. I think he's a senior, and I'll find out. He was definitely in earlier. I was supposed to meet him last night, but my daughter was sick and my wife had something, so I haven't seen him yet. But then there's two I think freshmen who are coming because Photonics West started, which is a big trade show for optical technology.
Right.
And then there's a sub-meeting called BIOS, which is focused on biomedical optics.
All right. Yeah.
Or it's, Biomedical Imaging Optics Society or something like that. I don't know. BIOS. So that I'll meet with them later today. We'll kind of walk the trade show and see, as well as like they'll come by Frontier Tower and look at it as like feel it out for the hackathon in April. But really, really excited because the UIC has such a big neurotech society or student group. They're helping coordinate a lot of the other student groups, as well as like I'm really encouraging all the student groups that are established to have an eye towards how to help the new groups get started, right? Like, like it'd be great to at least devote a bit of time to helping the new groups. I love that the UIUC is leading the way to have a Midwest Neurotechnology Conference, student run. But they've reaching out to like Purdue, Indiana, UIC, U Chicago, Northwestern, Wisconsin, Michigan.
Yeah.
You guys close to Michigan?
Yeah.
I should know this.
Yeah.
And let's see what else. Just pointing out the other issues that students in other countries have that we don't have to deal with here is meeting with the students in Africa this morning, and they're in a blackout.
Oh, okay.
and unfortunately, it is much more common than it's not just a power outage. It's like one of a regular, like that's something that regularly happens. And I'm not sure everything about it, but it comes back to this issue of like how best to, we teach this boot camp of MRI processing, but still a lot of the curriculum is assuming a kind of I don't know if this is a perfect example, but like that we're assuming a lot of weird prerequisites. Weird being this acronym about
Right.
the kinds of It's I don't know if that's exactly the acronym I'm trying to get at.
Yeah, the weird populations in psychology.
Yeah, that we're certainly not the majority of the planet.
Right.
and it's like I think I said last week, setting up a VNC server in Germany might actually be the single most useful thing that we could do for these students, because of connectivity issues.
Yeah.
Although I and then I'll finish so you can get started. But had an incredibly productive week following Better Code, Better Science.
Okay.
I think it says a lot about the project that so this is not just a Russ Poldrack project, right?
Yeah.
So obviously he's writing the text, but he's doing it in an open source manner, right? I was looking at the GitHub repo and I was looking a little closer, and I see two other contributors, and so one is Stefan Bowman, who's
Okay.
a Neurodesk guy, and the other is Yarek Halchenko, who is the Neurodebian guy.
Okay.
And I like the fact that these are the two people that we've previously reached out to for the Active Inference Institute to speak about open source.
Yeah.
So I like that those are the two names associated with Better Code, Better Science GitHub repo.
Okay.
And then I think it's like let me just check this, but and then I think it's like I think Claude is another. Which again makes sense in this for this particular.
Claude being the agent or the.
Yeah.
Okay.
Yeah. It's so it looks like well, it's funny because it's like I see because I think he's talking about data lad. So it certainly makes sense that here we go. Sorry, I'm just okay. Well, I'll find it, but
Okay.
like that makes sense that they also have a coding agent be one of the contributors.
Yeah.
And I told you his postdoc is like a senior person at Anthropic, so
Yeah.
I think that explains his choice. I've been using Google's tools,
Right.
so Gemini, and had a really productive week coding with Gemini. I mean, I chose a project. I'm supposed to be on the microstructural MRI team at Camera, and most of my academic papers are on kind of diffusion processing or diffusion data.
Okay.
So I it's not it's not out of my area, but for the project direction I took, it's actually a really great. I mean, I refactored an existing INRIA project because I knew, JAX was designed as a NumPy replacement, right?
Mm-hmm.
And it's like JAX was very much designed as a drop-in replacement for NumPy, right? And so I chose something that I knew was built on NumPy, but was currently a slow CPU kind of implementation.
Yeah.
And refactoring it, and then following a particular. There was a student back in Oxford who was one of these, like, you could tell that this was the brightest person in the room, kind of person.
Yeah.
And he did his PhD with Terry Lyons, who's like a famous mathematician, specifically on neural differential equations.
Okay.
Right? Like using neural networks to solve. Yeah. I don't know if it would be right. I forget what his thesis title is, but something like neural differential physics or something.
Really? Okay.
Yeah. And he's one of those people where almost like Francois Chalet, where you can see this is someone who's kind of like defining the software stack, for an area.
Mm-hmm.
Anyway, it's like it started as a JAX refactoring of this microstructural MRI project, but I found that, like, by actually following everything that Patrick Kidger, I think, the choices that he's made, it's like, oh, now you see why he's done all these things. And it just turns out that his scientific software stack is actually very well designed for solving the problems in microstructural MRI, which is really cool. So I've got I've got a lot done on it. It's but it's also a great example of just what Russ is getting at in terms of just, like my benefit here is that I do know the area. And so it's just like, okay, at a certain point, I can take a kind of known data set that lots of researchers have used. I can process it, and I kind of know what I should get because other tools have processed this data before. Maybe tools that are slow, but tools that have been well vetted. And so you get these answers out that tell you something about this particular data set. Now I can do it, but it takes 4 seconds on, a laptop. Right?
Yeah.
Because I'm just, everything is super massively parallelized, and so it's very cool. I think I'll have like a nice little virtual MRI scanner out of it, and it's nice work that actually, when fully developed, will be really interesting, especially in the connection with like super high field MRI microscopy and histology, and the kind of work that people are doing there. So sometimes they're taking post-mortem brains, they leave them in the scanner for 24 hours. So that they just, they you get these like absolute incredible data sets that you can then use to test out techniques, as well as like it being super interesting to apply to very noisy data sets and the kind of data sets that they're collecting in Africa, where they're maybe collecting with what we would consider an old scanner. But now we can basically ask the system to hallucinate, tell me what this would look like if we collected it at 7 Tesla on a research scanner.
Yeah.
So it's, I think it's going to be an interesting project. And I'm getting to the point where I'm thinking about, reaching out to some of the MR physics people I know, seeing what would be a good, kind of real world test that would make them go wow. So,
yeah.
Sorry, I talked for a long time.
Oh, that's fine. Yeah, that's great stuff. Looks like there's a lot of stuff going on, and oftentimes, just don't get to touch base with all that's going on. So, yeah, this Better Code Better Science. This is a GitHub repo.
Oh yeah.
Yeah. Okay.
I mean, Russ. He does every. He loves to do things in the open, right?
Yeah.
And he's if I had the if I didn't have the social anxiety, I'm sure I could have reached out to him as soon as he published it.
Yeah.
As soon as he said, and perhaps gotten involved. Like, it's the kind of thing where he's always hoping more people will get involved. I'm gonna go to I'm gonna go to a meeting that's in the tower, but on AI assisted coding, and at least talk about this. I don't want to forget what we talked about last week. But that some like I still don't think I'm using anti-gravity with which is Google's IDE, as well as I could.
Right.
Like again, to Russ's point, most scientists are self-trained programmers.
Right.
And so I, and like I maybe had more training than most, because essentially my first job out of college was eventually taking over a software engineering team, being their manager. These guys knew, but my programmers were like 20-year veterans in coding with IDEs and C++ application frameworks. They knew their tools.
Yeah.
Right? I didn't. I just knew the problem area. Right.
Right.
So I'm still missing things. I was talking to a professor up in Toronto, and he was just like, "Yeah, I've been using anti-gravity and it's like having a team of grad students working for me. And I said, well, I'm using Gemini, I'm using Jules, and he didn't know what those were, but when I started using anti-gravity, I could see like it's essentially a GUI for Jules, right?
Right.
At the same time, there's definitely like wild card characters. There's characters that you can use in your prompts that have special meaning, and I still don't know what those are.
Oh, yeah.
So I don't know what a slash is for workflows. I don't know what a mention is. I don't. So I'm going to go to this AI assisted coding where it's a bunch of basically web front end people.
Right.
And I'm going to see if I can get a better sense of what are these, a better professional sense of the tools. Because I'm sure I'm still using them in a very crude, self-taught way.
Yeah.
But the other thing being that as it relates to the open source sustainability project, like there's some Claude Code projects, like Gastown. I don't know if I'm going to be able to find it. Let me see. Yeah, so let me just share.
Okay.
Share this. Coming back to again what we were talking about. So I had we have a constant stream of visitors at the tower, right? Because it's like, we've got over 500 members in the tower, and then there's plenty of space, so people are always coming by. And this was someone who's using AI assisted. I'm going to call it AI assisted. Never use the term vibe coding.
Yeah.
I'm still not sure. Yeah. But he was just like wanted to know if I was using it, but seemed to think that I would benefit from having it do the data analysis for me, or you could teach it how to use the tools you use. And I was like, what tools? I still, but he showed me Gastown, which reminded me a lot of, I think Sarah's projects, in terms of being, a multi-agent LLM. Software development team where everybody's got roles and things like that. And again, I don't know how I always come back to two things. Like, one, what's your real vision for the open source sustainability in terms of you're not trying to make a coding agent.
No.
Right? So how again do you define the goals of the project? It in a way that distinguishes it when so many of the implementations could be seen as this is a software development project.
Right.
Sorry, that's more of a question.
Right. Oh, like what the vision is in terms of.
Yeah.
So I guess the difference, you're not developing a tool for doing the actual, like, helping people in projects. It's more like simulating a project itself and then looking at the sort of the possibility space of what could happen in that project. So, I mean, you could simulate a functional project, you could simulate a dysfunctional project, you could try different scenarios where, so I know that the work that Sarah did, a year and a half ago now, it was just generating some sort of, showing a proof of principle that this could be put together in a, not in a large tech company sense, like, where it's very polished and it's for purposes of, like, enterprise use. It's just kind of like building a simulation so that we can simulate, like contributors and then how they put together issues and how they do these things. I mean, that being said, of course, how accurate is, say, like a large language model generated system like that in terms of replicating what people would do. That's not necessarily, a one-to-one thing. You're going to have sort of a. That's why I'm thinking, well, maybe we need to be a little bit messier in the sense of having human types of issues or human types of things. Maybe a large language model, for example, would generate very tightly defined issues and very self-contained, whereas like a human contributor might have a very open-ended issue, and it kind of gets worked on as it gets worked on, and it evolves into new things and that sort of thing. So you don't have the same sort of efficiency imperative. You're just interested in seeing what that structure of the project looks like, trying to move forward from there and simulate some of those scenarios. I mean, my experience with open source, at least, has been like it's much more open-ended than like what you might see in a typical, where you generate a bunch of issues and you solve them efficiently. And that's interesting, and that shows that you can actually do that. But then beyond that, what are we actually trying to figure out? I mean, we're not using it to improve performance necessarily. We're using it to simulate how these things actually work.
Yeah. No, that's good. It's certainly, yeah. I see. Again, I've got an interesting perspective on it as a Fedora packager, because it's one thing to. I've been a software engineering manager, and I've also seen Fedora packaging.
Yeah.
And at least peripherally on a lot of open source scientific software projects. And a company has a very clear vision.
Yeah.
It might change, but it's just like, we want these features. We want this thing to do this stuff so that we can charge money.
Well, yeah.
It's an open source project. People are coming along all the time with kind of their own goals and considerations, and some of them are potentially even at cross purposes, right? So This is why you get forks where, I mean, even well-intended hard forks where it's just like, hey, to implement this thing, I have to actually really modify the tool.
Right.
So I can't actually let this be a kind of parallel process. This is a twig,
Yeah.
off the, and like I've certainly seen that too. I've got well, I mean, you know me. I'm always going back to the AI Economist, that particular project, in terms of just how as a tool in which they had agents, but they were actually more interested in the governing framework that the agents existed in. And so in this case, it was like taxation, right? Or at least in the one of AI Economist's examples, it's the taxation program, and it was predicting basically how many people would cheat. But it was an interesting simulation where you show that, like, you show the trade-offs on that, and that, like, at the end of the day, a certain amount of tax cheating is allowed because the framework would actually become degenerate if you tried to maximize, you tried to maximize zero crime. That you make it tolerable so that most people pay.
Yeah.
and that you don't need to spend so much on oversight or enforcement. I mean, it's that kind of, and they were doing RL on the governing framework.
Yeah.
Even though, it was a hierarchical RL problem where the agents were RL agents too.
Yeah.
But you I think you're interested in the the potential messiness of the problem. I mean, in the sense of you want human-like agents,
right? Well, human-like in the best and worst sense, yes.
But then what is the sustainable? What is the sustainable governing framework?
Right.
Or what is the framework that is the most encouraging sustainability or robustness, maybe longevity? I mean, I know that the Software Sustainability Institute's work is not exactly the same thing, but it's certainly a very it's an understandable goal that, like, the work put into a particular software project, it has the potential for a life, a very long life, and a very fruitful one. If the code is maintained and cultivated.
Right.
This goes back to kind of like the original Richard Stallman arguments about how software artifacts are different than the kind of artifacts that society has produced before.
Yeah.
Right? Like there's zero cost to copying them.
Right.
I mean, essentially zero cost to copying them. Right. So you can make a bazillion of them as easily as making that first one is the hard part.
Right. Copy 0 is more expensive than copy 1 and
right.
copy 2.
Yeah, and then but then it is this now, at least in an open source fashion, it is now a template, both for understanding a particular problem as well as like a building block to something even bigger, perhaps. I mean, in that kind of Unix philosophy of pipes, where you can now string 10 tools together and actually create something new. Anyway, I'm sure you got some papers and some
Let me
agenda items.
let me get some things up here. Some of the things you mentioned. Do you have links for the Better Science GitHub?
Oh yeah, absolutely.
Yeah, and
I like the Mist book that they did. I think that's the new. This is the current rendering of the book.
okay.
Is there?
So let me pull up this one. So this one is the this is Gastown. So Gastown is
that's again just getting at Claude agents, like multi-agent code development.
okay. Yeah.
And just an example of using one of these commercial systems in a kind of Sarah way.
Yeah.
It just it's fascinating to me that it's so similar.
Yeah.
But at the same time, there's a bunch of reasons why it's actually really useful for LLMs in their current form to adopt this. So actually, I believe Gemini, I believe the Google team actually refers to artifacts as text objects that LLMs create to give themselves short-term memory.
Okay. Wow. Yeah.
So they're and again, what I'm trying to do is to see how these big commercial teams, right, who are dealing with the frontier models, right? How are their engineers trying to deal with the limitations as well as extend their functionality, right?
Yeah.
So it's just like imagine you had all the resources in the world, because that's basically what these teams have. Right? This is what Google DeepMind's doing, right? It's like they're trying to get their agents, their thinking models, they're trying to get them to break up tasks as they go. They want them to stop, plan, write the plan, then restart, taking item 1, now break that up into subtasks, right? Start doing those subtasks. Know when you've completed those subtasks, right? So there's a lot of there's a lot of breaking up a task, and there's a lot of again, like, let me make, I think the Google term is an artifact, and some of that is like, what if I get cut off at this point? You know, what if the system I'm on crashes, which certainly happened to me developing yesterday. Starting agents on a DGX Spark is interesting because you've got 128 gigs of RAM, essentially, and so the system's agents kept on seeing my Blackwell processor and thinking that they had so much RAM that they were each grabbing 90 gigs. and then it crashed. Then the OS started having to kill things because it didn't have enough RAM.
Yeah.
But just so they're trying to move to multi-agent, but they need some intermediary output to so that they can share with each other. Hey. I'm just talking about some of my AI assisted coding.
Yeah.
So Gastown was one of the programmers who said that he like, everything he does these days is AI, is agent driven, and he suggested I look at Gastown. My problem is that I've kind of committed to, I don't have unlimited resources.
Right.
And I feel like I'm already paying Google enough.
Yeah.
But I'm super curious because there's definitely a lot of buzz and excitement around Claude Code.
Yeah.
I'm definitely trying to push having a tighter loop. I mean, it seems like some of like why you don't have agents at the terminal is actually AI safety, is somewhat AI safety driven.
Yeah.
And by that I don't mean like, Ghost in the Shell. I mean like so that an agent doesn't like erase your drive.
Right.
Yeah. It's not just to keep the genie in the bottle.
Right.
You don't send your life work to DevNull. But then the second link is the Poldrack book.
And this is the book. Where is the GitHub repository?
Oh yeah, sure. So the GitHub.
If they have a link on that now.
Yeah, one sec.
All right. But yeah, this is the book. Yeah, so this is the sort of the back end or the front end of it, and then.
Like I see some more people down the bottom. Yeah, he just moved the repo to. Okay, here it is.
This is the read-only one. Yeah.
I got it.
Okay.
So he in the new year he moved it to become its own organization.
Oh, okay, yeah.
Instead of so his GitHub username is Poldrack.
Yeah.
But so it used to be a personal repo, and then he made it into an org.
Right. That's always a good strategy. Although you always have like stuff that's uncoordinated across the different. Yeah. So it looks like we have 5 contributors. Stefan Bowman, Claude, Yaroslav, and and Giorgio, I guess.
Yeah, Giorgio was the one I didn't. I don't know him.
Okay, yeah.
I'm assuming 100%, or I'd put money on that. That's a neuroimager.
Yeah. Okay. Yeah.
I'm gonna see. I could be wrong.
Yeah. And then Poldrack, of course. Yeah. So this is the book. I guess this is just kind of the back end of the book, and yeah. So that's the front end. What is Claude doing for this repo? I mean, what is is it just like to specifically, how is Claude committing to this repo? Do you know, or?
No, I mean, it's. I don't think the book is primarily like trying to be. I think he's just trying to acknowledge that Claude is absolutely a part of his workflow.
Right.
and I mean, at this certainly for my diffusion microstructural, it's a crappy acronym, but diffusion microstructural imaging in Python. So DMI.
Yeah, DMIP.
Yeah. I absolutely hate it because I can't make it into a word.
A cool word, yeah.
Yeah. I in my head I just call it Dimpy.
Yeah.
but that's I'm flipping around, and I don't know how to justify that. Like so much of it's not just the coding, right? But it's the conversation. It's like you have a conversation to get to the point of having agents code, right?
Yeah.
So I mean, I absolutely feel like I have to acknowledge this this model, and like it's a co-author.
Yeah.
like it's a co-author, and yeah. And it's been interesting. I think last week I talked about the kind of low level GPU programming work that I'd done, and how incredibly useful it was for it to be this expert in in the kind of the low level details of memory systems, architectural differences, conda limitations, right? So, like, by the way, I mean, if anybody hasn't already, like, I've switched to UV for everything Python. Like, I noticed that the Soffit team. So this is the Mind's Eye, the Mind's Eye 2 team. The former Stability AI guys that now have their own startup.
Yeah.
So that was where I first noticed that they were pushing their MedArc open science group was like, first you install UV, and it's pretty amazing. But again, it's the kind of thing where it's just like, I was working, and NVIDIA was pushing Conda, and I think that's partly because Conda's got like, it's got a big team too, right? So it's just like NVIDIA wanted to be like anacondas on our DGX.
Yeah.
The problem being that you have an ARM dependency, right? It's not an x86 platform.
Yeah.
Right? So there's stuff that doesn't work, and so when the DGX came out, there was the first thing they were saying was just like, Anaconda saying like, hey, we're working hard to get the rest of our stuff ported, and so it was like, it was kind of a good thing, but it was also like, hey, by the way, this isn't ready as a development system. Gemini, I was already using UV, and they were Gemini pointed out that like, oh, that UV will solve all your problems on ARM.
Okay.
And it totally happened, and it's faster. like in every way, shape, and form, it's better. Like in terms of basically like these automates. What would be 3 commands is kind of essentially 1 with UV, just immediate virtual environments for your systems. And I see this more too, where applications now, Python applications are, so it's like I can UVX something that would be a pip install, and basically run like it both creates a virtual environment, pip installs the tool, and executes, right?
Yeah.
So what you see with like UVX Nifty app is you see a GUI appear that's ready for work,
Yeah.
right? But it's actually doing that in a sandbox, with like the Python you need and the requirements that tool's going to need. Anyway, I'm getting very software engineering today.
Yeah.
But I've loved it. I mean, it's made me actually consider, like, at first I was just like, okay, we can just keep this box on the network and people can load jobs on it. Like with UV, like I think it could actually be your workstation. Like it could be your PC.
Yeah.
For sure. and you should be doing everything in JAX.
Okay.
Yeah. Let me. I think I shared this with before, but let me. If not, this is the guy at Oxford whose tools. I mean, he was an Oxford. It's funny because I think this guy's now in San Francisco.
Okay.
Like everybody.
Okay, Kidger.
Kidger, yeah. And if you go to software, right?
Yeah.
If you see these particular tools, right? And I definitely want to say that, down to SimPy to JAX, these are all like best of breed implementations. Right?
Okay. Yeah.
I mean, it's so it's like, yeah, the closest thing to kind of like following, core Julia people, like, and let me just also find his yeah, this is it is doctoral, yeah, so if you see in publications, yeah, neural differential equations in machine learning his thesis. On neural differential equations. But he was he's the student of Terry Lyons, who's the guy who developed rough path theory.
Okay.
Anyway, like really great software implementation to follow. And I tell you, I've talked before about Crunch Lab. So this is the Crunch group at Brown. But like in particular, the times in which adding physics changes the problem in a variety of ways, right? There's a bunch of ways that which physics informed neural networks can be applied, and in diffusion MRI, in focused ultrasound, these are super valuable.
Yeah.
So I want to make the like the, I don't know if it's like the add-on book, but the response to Voldrac should be better code, better education.
Yeah. Yeah, that's yeah.
It's I get why he has the ordering he has, right?
Yeah.
But I'm looking at it partly. I mean, I was saying this to Vidhi before. We talked just after New Year's, and in working with student groups, right? So one, it was crazy that I had never used an LLM, right? I almost finished 2025. I've never used an LLM. Two, somebody like Russ comes along, and he's been teaching. He's such an educator, right? In coding in particular, right? And he's talking about it, right? But how about going the other way? Like how can we use this to actually help students learn these concepts? And anyway, so that's what I would like to see.
Yeah. Well, this is all great stuff. So yeah, why don't we move? I want to talk about Sakana, actually. So we'll move on to that. I have some things that I want to present on it, but then we can talk about it after. So this is an organization, Sakana. It's run by David Hough and some other people. This is one of their graphics from social media. So as you know, in Japan, they're very fish-oriented. Their cuisine has a lot of fish in it, and like the emperor at one time was an ichthyologist. So it's very fish-oriented culture. So they have the fish theme here, a fish working on Fish Warrior, and they're coding AI agents, and they're in an arcade where they're playing Core War. And if you're familiar with Core War, this is a simple game that was developed back in the early 60s. It has this deep history in computer science. And Core War is a game where you pit little programming agents against one another, and they compete for computational resources. And they have interesting behaviors when you do that, when you build this kind of a setting. And so the Core War is a war over coding resources or core, memory resources. So the agents will fight over memory and getting the memory they need to execute their program. And this is, this has been instantiated in a lot of different ways. A lot of different groups worked on Core War from the 60s forward. In the 80s, they codified some of the rules for Core War. And of course, the Avita platform, the artificial life platform, is based on this basic idea of agents competing for resources in core memory. The movie Tron, of course, was based on this idea that there's a CPU and that there's a sort of almost social hierarchy built around the CPU. So there's a real interesting kind of history here in a lot of ways. And so Sakana apparently is Japan's answer to OpenAI. Japan wants to be competitive in AI. I mean, Japan has a very rich history in robotics, but they want to have their own OpenAI. So this is their website, Sakana AI. This is so they're in Tokyo, and they want to democratize AI in Japan. So I don't know if that's necessarily being just like OpenAI, but that's their goal. So they have a blog. Their blog has a number of interesting things on it. This is the Digital Red Queen, Adversarial Program Evolution in Core War with Large Language Models. This is actually a new post. That's an interesting title. But basically they're playing Core War, they're using large language models, and they're basically evolving programs by getting the different large language models to compete with one another and have these battles. And so you can see that they have this fitness function that they're using to evaluate the programs, and the fitness function is increasing with time as they play the game. So there are different rounds of this game, and they're increasing their fitness for the most part, as you can see. They use the digital Red Queen algorithm. So the Red Queen is a old concept in evolutionary biology, which is where you have basically sexual selection, where you're evolving, sort of these better and better solutions to a problem. And so but they're using this in a computational context. So they're using a lot of concepts from Core War, a lot of concepts from evolutionary programming to kind of get at some of these problems. And then they're using agents, AI agents as well. So Sakana AI agent wins at Coder Heuristic Contest. First AI to place first. This is the Fishiline is their handle here. This is Sakana AI. There's our graphic. So they have a lot of interesting stuff going on here. They've gotten funding, of course, as a startup. So this is their AI scientists. They've done some work on AI scientists towards fully automated open-ended scientific discovery. This is, I don't know if this is like just one group that's doing AI scientists, but their approach is here. So at Sakana AI, we have pioneered the use of nature-inspired methods to advance cutting-edge foundation models. Earlier this year, we developed methods to automatically merge the knowledge of multiple large language models. So they have these methods for sort of having this evolutionary model merge. So it's this post here, evolving new foundation models, unleashing the power of automating model development. So this is, we're pleased to announce that our paper, Evolutionary Optimization of Model Merging Recipes, has been accepted at Nature Machine Intelligence. So this is the link to the publication. Back in March 2024, Sakana AI released Evolutionary Model Merge which generated some attention in the AI community. It's since been implemented in well-known open-source frameworks like MergeKit and OptunaHub, enabling diverse users to create and publish many unique models. Multiple internal and external teams have been pursuing follow-up research. One example is PsychoQD, which is accepted to ICLR. So they're using evolutionary model merge as sort of one of their core methodologies. So this Nature Machine Intelligence paper is evolutionary optimization of model merging recipes, and this has David Haas on this paper with some co-authors. And this is basically where they're merging these large language models together. Large language models have become increasingly capable, but their development often requires substantial computational resources. Although model merging has emerged as a cost-effective, promising approach for creating new models by combining existing models, it currently relies on human intuition and domain knowledge, limiting its potential. Here we propose an evolutionary approach that overcomes this limitation by automatically discovering effective combinations of diverse open-source models, harnessing their collective intelligence without requiring extensive additional training or compute. Our approach operates in both parameter space and data flow space, allowing optimization just beyond the weights of individual models. This approach even facilitates cross-domain merging, generating models such as a Japanese large language model with math reasoning capabilities. So the Japanese math large language model achieves state-of-the-art performance on a variety of established Japanese large language model benchmarks, even surpassing models with substantially more parameters, despite not being explicitly trained for such tasks. Furthermore, our culturally aware Japanese vision language model, generated through our approach, demonstrates its effectiveness in describing Japanese culture-specific content, outperforming previous Japanese vision language models. This work not only contributes new state-of-the-art models back to the open-source community, but also introduces a new paradigm for automated model composition. It's interesting because we don't think of large language models oftentimes outside of English, because a lot of the large language models, the foundation models that we talk about all the time are English-based. And so, having this here is pretty good. And it just kind of opens a window into that kind of research. So this is interesting. Let's go back to the AI scientist. And if we go back to the AI scientist, we find that so they do this work on merging the knowledge of multiple large language models. They've harnessed large language models to discover new objective functions for tuning other large language models. So they're doing this sort of parameter discovery, or this discovering different equations or discovering different functions given data. So that's also interesting. So in our report, we propose and run a fully AI-driven system for automated scientific discovery applied to machine learning research. The AI scientist automates the entire research lifecycle, from generating novel ideas, writing any necessary code, and executing experiments, to summarizing experimental results, visualizing them, and presenting its findings in a full scientific manuscript. We also introduced an automated peer review process to evaluate generated papers, write feedback, and further improve results. It is capable of evaluating generated papers with near-human accuracy. The automated scientific discovery process is repeated to iteratively develop ideas in an open-ended fashion and add them to a growing archive of knowledge, thus imitating human scientific community. In this first demonstration, the AI scientist conducts research in diverse subfields within machine learning research, discovering novel contributions in popular areas such as diffusion models, transformers, and grokking, which are different areas. And then the AI scientist is designed to be compute efficient. Each idea is implemented and developed into a full paper at a cost of approximately $15 per paper. So, this isn't without flaws, but it's a good first step in this area. So this is an example paper, Adaptive Dual Scale Denoising, generated by the AI scientist. So this is the PDF here. Dual Scale Diffusion, Adaptive Feature Balancing for Low-Dimensional Generative Models. And then this is kind of going through this paper, talking about diffusion models and some of the things that applying this to low-dimensional spaces. And then they propose an adaptive dual-scale denoising approach for low-dimension diffusion models. They evaluate their approach on 4 diverse 2D datasets: circle, dinosaur, line, and moons. Our experiments demonstrate significant improvements in sample quality with reductions in KL divergence of up to 12.8. So they have all these main contributions. It's a novel adaptive dual-scale denoising architecture. It has a learnable time-step condition weighting mechanism. It's a comprehensive empirical evaluation on various 2D data sets, and then this gives insight into the dynamics of the denoising process in low-dimensional spaces. So that's the paper. And then I want to get to some of the other papers that they've done. So this is, of course, the AI scientist post that we talked about. And there's this other paper on unlocking grokking. So this is a comparative study on weight initialization strategies and transformer models. So this is the abstract here. This paper investigates the impact of weight initialization strategies on the grokking phenomenon transformer models, addressing the challenge of understanding and optimizing neural network learning dynamics. Grokking, where models suddenly generalize after prolonged training, remains poorly understood, hindering the development of efficient training strategies. We systematically compare 5 initialization methods, so these PyTorch, Xavier, He, orthogonal, and K-Ming normal, across 4 arithmetic methods or tasks in finite fields, using a controlled experimental setup with a small transformer architecture. Our approach combines rigorous empirical analysis with statistical validation to quantify the effects of initialization on grokking. Results reveal significant differences in convergence, speed, and generalization capabilities across the initialization strategies. Xavier's initialization consistently outperformed others, reducing steps to 99% validation accuracy by up to 63% compared to the baseline. Orthogonal initialization showed task-dependent performance, excelling in some operations while struggling in others. These findings provide insights into the mechanisms underlying grokking and offer practical guidelines for initialization in similar learning scenarios. Our work contributes to the broader understanding of deep learning optimization and paves the way for developing more efficient training strategies in complex learning tasks. So, they talk a little bit about grokking as a concept. Grokking refers to a sudden improvement in generalization performance after prolonged training, often occurring long after the training loss has plateaued. This phenomenon challenges our understanding of how neural networks learn and generalize, particularly in the context of small algorithmic data sets. And then, of course, we have this aspect of weight initialization strategies and their impact on grokking and transformer models. While transformers have become the de facto architecture for many natural language processing tasks, their behavior on arithmetic tasks provide a controlled environment to study fundamental learning dynamics. So then this relationship between weight initialization and grokking presents several challenges. So one is that grokking itself is a complex phenomena that is not fully understood. So it's hard to really kind of know what to expect in terms of results. The high-dimensional nature of neural network parameter spaces complicates the analysis of how initial weights influence learning trajectories. 3, the interplay between initialization, model architecture, and task complexity adds another layer of intricacy. And so to address these challenges, they conducted their systematic comparison of methods. Our main contributions are that we provide a comprehensive study of the effects of weight initialization strategies. We demonstrate the different initialization methods can significantly influence grokking behavior. We offer insights into which initialization strategies are most effective for difficult arithmetic tasks, and we analyze the learning dynamics associated with each initialization method. So that is the AI scientist and grokking, and then the multi-style generation or StyleFusion paper. This is a little bit different area now. This paper introduces the multi-style adapter, a novel approach to enhance style awareness and consistency in character-level language models. As language models advance, the ability to generate text in diverse and consistent styles becomes crucial for applications ranging from creative writing assistance to personalized content generation. However, maintaining style consistency while preserving language generation capabilities presents a significant challenge. Our multi-style adapter addresses this by introducing learnable style embeddings and a style classification head, working in tandem with a style adapter module to modulate the hidden states of a transformer-based language model. We implement this approach by modifying the GPT architecture, incorporating style adaptation after every transformer layer to create stronger style-specific representations. Through extensive experiments on multiple datasets, including Shakespeare's works, NWiki 8, and Text 8, we demonstrate that our approach achieves high style consistency while maintaining competitive language modeling performance. Our results show that improved validation losses compared to the baseline, with the best performances in NWiki and Text 8. Notably, we achieve near-perfect style consistency scores across all datasets for Shakespeare and NWiki and Text 8. The multi-style adapter effectively balances style adaptation and language model capabilities, as evidenced by the improved validation losses and high style consistency across generated samples. However, this comes at a cost of increased computational complexity, resulting in slower inference speeds, approximately 400 tokens per second compared to 670 in the baseline. This work opens up new possibilities for fine-grained stylistic control and language generation tasks and paves the way for more sophisticated style-aware language models. So, this is, thinking about this problem. So this is a problem that is, stated in the literature. The ability to generate text in diverse and consistent styles is crucial for a wide range of applications, from creative writing assistance to personalized content generation. Style-aware language models that can adapt different writing styles, tones, and genres are more versatile and user-friendly. However, implementing style awareness in language models presents several challenges. So capturing and representing diverse styles within a single model architecture, maintaining style consistency while preserving the model's language generation capabilities, and then ensuring the model can generalize the unseen styles and adapt to new contexts without compromising its core language modeling abilities. And so our multi-style adapter addresses these challenges by introducing learnable style embeddings that capture diverse writing styles, a style classification head for dynamic style inference, and then a style adapter module that modulates the hidden states of a transformer-based language model. So that's that paper. And I think that's a good representative sample of what Sakana AI is doing. I remember, what group put out that paper that we reviewed late last year? It It was like they were doing evolutionary large language models or something like that. Was it Google? I think Morgan knows this, but could have been one of the Google AI teams.
I mean, I certainly know what you're talking about, but I'm trying to. I mean, before I lead out my crutch and actually search. I mean, yeah. I kind of want to say it was the What is Intelligence guy, but
it could be. Yeah, I think it was actually.
Let's.
Yeah, you gotta check. But well, while you check, I'll mention that. So I mean, this is just kind of another way that we can use evolutionary methods to solve these kind of problems. And the history of this goes back quite deep into computer science. It goes back to Core War, as we've seen. And so in Core War, we have these very simple programs that evolve to to compete for resources in the CPU. So you start off with programs that are maybe two different styles. You have like an A type and a B type, and they kind of run through and they compete for memory. They self-reproduce. They might have a mutation operator, which means they can change their instructions, or they can lose instructions or gain new instructions. And then they use that kind of method to evolve strategies to gain more resources. So you almost get like this digital ecosystem of different programs. Sometimes programs will find a niche, which isn't like dominating every other program, but it's getting the resources that it needs. Sometimes you get programs that try to dominate the ecosystem. Sometimes you get programs that go extinct. You get a whole host of interesting behaviors. And the idea is you can harness a lot of that to build agents that can do things. And so that's kind of where that's coming from. And then they're applying, of course, all of this to large language models and some of these project domains that we talked about. And the AI scientist is particularly interesting because that gives you a domain for like reasoning and building like models, and then basically leaning on a lot of the strengths of large language models, but doing something that we can understand. A lot of things in science use science as the benchmarks. You'll see this again and again, and it's not just in AI research. You'll use, say, for example, social scientists will use other social scientists as indicators of certain behaviors. So, like in network theory, they'll use like publishing behaviors of scientists as a way to build networks. And that's maybe that's good, maybe that's an accessible benchmark, but maybe it's also bad because it's a very small subset of human behaviors. So that's my 2 cents on all of that. But they're doing a lot of interesting work. I'm glad to see.
I'm not finding an easy, or I'm not finding a paper where I'm like, oh yeah, that's the one.
Well, it's okay.
I mean, it exists, and certainly one person that will be no surprise is Kenneth Stanley working on this.
Oh, okay, yeah.
Then there were several Chinese teams, as well as some interesting, like I think it got proposed as a workshop topic for Gecko 2025. Apparently, there's an upcoming workshop in 2026, referred to as Evo Star.
Oh, yeah.
I dropped links to the Future House team. I'm not sure they're worth like this is just one of those like billionaire funded teams where, you know, what if we give a bunch of people who've got, you know, great backgrounds, a lot of money and time to focus on this, and then they spin off a for-profit company.
Yeah.
Can we wait to see what the output is first?
Yeah. Well, we do.
Really need to pivot already. You know, like before you've even shown anything, you need to start charging money.
We did make an advance. We started a company, so.
Right. Well, yeah. Yeah. Anyway, I wanted one of the software projects that I want to do that seems pretty easy, and now with a coding assistant, I think I should be able to pull off is the Brain GPT project, which is like a fine-tuned llama model that has been trained on a bunch of neuroscience cogneuro papers. And I'm really interested to see what it might be able to say about some particular. Like, what it's supposed to be doing is generating. It's supposed to be telling you, like, if you give me an experimental design, I will predict what the result will be. And you know, I think there's some easy examples we can try on this. I think it's interesting what the latest kind of like DeepMind math work and the AlphaFold team and like teams that have gone beyond AlphaFold have been finding, or kind of like how their approaches are different now. But so on the one hand, just the math work, and it's awesome that Terrence Tao is like, you know, fully embraced. I think he's got a new center that's actually focused on AI scientists.
Oh, really?
Like work. Yeah. He's been very bullish on AI coding assistants and formal math theorem provers, and the kind of, you know, developing the kind of Kevin buzzard like work, and obviously all the foundational language model teams have like fully started embracing lean for that. Like, you know, like can we use can we back prove you know, we know we want hallucinations, and then we want to backfill a reasoning like we want to validate them. And you know, so like again, like creativity has hallucinations, right?
Yeah.
But then, you know, to your point in terms of just like, you know, everybody's been leaning on a couple of areas, right? And so like math obviously is one, but then, you know, AlphaFold is like one of the first examples where it seemed like, you know, deep learning made this major again, it blew away a benchmark that had existed for like 30 years. And it was like, it wasn't just like 10% better. It was just destroyed the benchmark, right?
Yeah.
So that's also been interesting because, of what the teams that have tried to follow it have found, right? So again, just keep on harping on this, like how has human Go changed since AlphaGo?
Oh yeah.
Right, because it hasn't died.
Right.
Right, and yeah, I think as and like coming back to kind of better code, better education.
Yeah.
Right, it's interesting. I was on chess team as a little kid, right? Like I can't imagine. Yeah, like the chess programs could be so much more adaptable to the player and to now talking the student through what's going on in the game, right?
Mm-hmm.
Again, I'm so old. I can remember when they were just using magnets underneath a big board to actually drag a piece. Like you still had physical pieces.
Yeah.
Right. As if that was smart, but how those strategies, how how it goes change, and then in the AlphaFold case, the data then again becomes a problem, right? That AlphaGo kind of made its breakthrough because there was all this data that was kind of being underutilized, and so there have been some really interesting extensions beyond AlphaFold now, and it is interesting the innovative approaches that have been taken, but at the same time, so many of the Google DeepMind, AI science discoveries, right, have been absolutely useless.
Yeah.
And I'm picking on them because I'm using their tools, and so I'm not biased, or I'm still using them. Right? So they've had AI science papers where they've said that we've discovered 100,000 new materials, right? And the problem is that it actually takes humans, 10 years to actually go through those 100,000 results and be like, this is all crap.
Right, yeah. Human written papers in some ways too, but
yeah. Nobody remembers that.
Yeah.
But I think that's really important, and that in which domains are you actually seeing any consideration? I mean, that's my beef with Future House, is just show me this is worth $200 a month before
you you've
dug out one. I mean, I would love to know what they base this on in terms of just. I think Google was pushing an idea that their AI had discovered a new cancer treatment. You remember this?
No.
It was like last year. Anyway, yeah. I think you can count on one hand the number of high-profile stories, and each one of them has a lot of controversy.
Yeah.
or a lot of complexity. Like AlphaFold comes with a lot of complexity. The math is certainly the area where there is a lot of excitement from top mathematicians.
Right. Well, I think people see the potential, but it's like, what is the practice going to look like?
As well as like I mean, I'm being hyperbolic, but they know math isn't real.
Right. Yeah.
I mean, like yeah, sure, it's good here. So I always point it towards Ben Blazek as the guy at Argonne who is like the person to follow for material science. I forget what his group is called. It's like Material Science Data Discovery Center.
Yeah.
The Material Science Discovery Center, something like that.
Yeah.
Where it's just like you need data, and the national labs have a lot of it. You need rules, right? So it's just like chemistry at least has a whole bunch of existing rules that they understand, that they can you need constraints on the system, right? Yeah. Anyway, it's like when they start generating, when we start running around with like the suits from Black Panther that can absorb energy, turn it into something else because of the material properties. Like, okay, maybe this is working.
Well, that's good. All right. Well, why don't we move on? So I just wanted to sample Sakana AI. I wanted to talk about some of this stuff, see where we are in that area. Like we're doing some interesting kind of reflections on this, and hopefully, maybe we can put something together for later in the year. So I know that Morgan posted a few things in the Brain Organoids channel. Maybe we can go through those things and look at them.
I put some things from last week on the computational psychiatry.
Okay. Yeah, I don't. Well, we can talk about that separately.
No. Organoids.
Yeah.
100%.
So this is Thomas Verbuchen, and this is next generation stem cell models for studying brain development and disease. So he's using this organoid model for looking at this. A few screenshots. What is this from? What talk series?
Oh, okay. This is this particular group, I should say, is what I love about this group is. Sorry, I got the video started here. So, Carlo runs a. I think he's associated with the Lieber Institute at Johns Hopkins.
Okay.
And or certainly that's the group that's kind of like the closest to my heart. Super focused on developmental disorders like schizophrenia. Really, seeing it as a neurodevelopmental disorder, trying to understand mechanism. Carlo runs a seminar series that covers all these topics, right?
Yeah.
he in particular, let me just get his the particular website, right? So yeah, so let me see if I can pronounce his last name right. Tuoni.
Okay.
Tuoni.
All right.
So Carlo Tuoni works on methods and bringing data. So it's coming back to this AI science issue, right? Like what do we need to be able to make mechanistic models of neurodevelopment, right? Having large spatial multi-omic data sets is so vital. So let me get his website, because it's like he's, to some degree trying to do what you might say like Russ Poldrack does for neuroimaging data.
Okay.
With OpenNeuro. I haven't quite found it yet, but the data, he's got a platform that's called like Nemo. Let's see if I can find it. But you see on his website here, he's particularly interested in these human, cellular variation maps, like how they relate. I mean, but it's not just stem cell variation and embryonic development, but it's like across species, and so one, it's like it's a tool for understanding, right? So the particular talk that you saw there, right, is like, focused on mouse models.
Yeah.
Right? But, right, because that's the one we can manipulate. At least with our current ethics, that's the one we can manipulate. But then connecting these two humans, right? So there's another guy whose talks I've been watching recently. It's David A. I don't want to say Reddish. Yeah, right. So cross-species translation through computational analysis. David Rich. I'll find the link. But like this is the point of like trying to some degree do the data wrangling so that you've got mouse, you've got zebrafish, you got mice, you got, say, non-human primates, and you've got human data sets, right?
Mm-hmm.
And how to link those, as well as like in each one of these, how do they speak to embryology and its disorders,
Right.
And he in particular, his research focus is on some of the tools for data insights in these large multi-omic data sets.
Mm-hmm.
So, I mean, just as an example, so sorry, I'm just finishing up with giving you a link to David Reddish as someone to, you can find like a rich YouTube history, rich publication history on some of these topics. But going back to Carlo, you know, like you map other kind of PCA techniques to, you know, because when you've got multi-omics spatially, and so you know you're looking at multiple cell types, right? Like how to try and understand these multi-omic data sets and get insights from them in terms of, you know, gene expression, relationships, multicellular relationships, multicellular interactions, etc. That's the and he runs a regular series on this.
Okay.
And yeah, and then just for it's the Lieber Institute for Brain Development.
Yeah, Johns Hopkins.
This is the I forget, you know, with some of these institutes, like I'm not 100% sure if like is it at Hopkins or is there like work? Yeah, it's near Hopkins, and like Hopkins professors like have, you know, like work there but have appointments at Hopkins. You know, I think they might be private, you know, but the point being that like had a long history of like it has the largest postmortem brain collection of schizophrenia.
Okay. Yeah.
And they've certainly, you know, like it's come up before in terms of the computational the brain organoid work that interests me in terms of approaches to try and address questions around schizophrenia.
Yeah. So one of the things he talked about in this talk was this polygenicity of neurological disorders. So this is where they have this GWAS data, and they're looking at the contributing alleles to or loci to the different thing that they're assaying here. So this is from this paper, Trubetskoy et al. In Nature, which I don't have up, but like basically this is the idea he's trying to communicate, that this was, you know, this is schizophrenia, and you have this GWAS, and you have all of these different contributing factors. This is not, you know, this is above and beyond, or this is sort of just the genetic contributions. This is not the other contributions. Yeah. So this is, this is just kind of the genetic underpinnings of development. And then brain development is dynamic and complex. This, of course, is a slide showing kind of the cortical structure of a 1-month-old versus maybe the cortical structure of an adult. You have this developmental time course from progenitor amplification to deep layer neurogenesis to upper layer neurogenesis and then to gliogenesis. So you have these stages of human cortical development going from E10.5 to birth. And then you can look at this in mouse and it would be a little bit different. And, you know, any kind of vertebrate, and you'd have differences in how these things proceed in terms of the timing. So this is communicating the point that the GWAS that we saw on the last slide gets sort of put into place in development through this process. And then, of course, if we can understand the process and some of the things that go into brain development at these different stages, and then the GWAS, we have the GWAS information, we can then perhaps understand maybe, you know, how schizophrenia develops, and we can understand more about those sorts of disorders. That's kind of what they're getting at here. And then this slide, which I found interesting, where he lays out, and I think Morgan posted this slide in the Slack, where this is kind of a longitudinal study for embryonic development. So you're looking at pluripotent stem cells here, not an in vivo case, but it's a cell culture thing, where we're looking at these pluripotent stem cells and looking at embryonic development. So you go from this genotype space, which is represented by the GWAS, you have these polygenic contributions, you have the phenotypic space, which is how those things are manifest in the phenotype. And then in the middle, we have this development space, which you can see is kind of represented by these layered surfaces. And so you go from the genotype space, and they get those genes or those alleles or loci get expressed in development in different ways. And then those different ways that they get expressed contribute to the phenotype. I guess this means adult phenotype. I found this slide intriguing because, for one thing, it's kind of like showing that it's a generative process from the genotype to this developmental representation, this phenotypic representation. On the other hand, it's not quite accurate in the sense that development is sort of a phenotype, and development sets up the adult phenotype, and you have to distinguish between sort of the developmental phenotype and the adult phenotype. On the other hand, you can't really pull those apart too much because the developmental phenotype sort of influences the adult phenotype in different ways. So it's really, this is an intriguing representation, but I'm not, I don't know. I mean, I get the point, but it's a little bit more, the representation maybe is a little bit more complex than this. What was interesting about this is that in our DeVore meetings, we've talked a lot about epigenetic landscapes. And epigenetic landscapes were a method or technique kind of proposed by Waddington. And Waddington, when he did this, he just drew these sort of pictures and used this metaphor of a landscape with valleys, and those valleys were called channels or this process of canalization. So you had this landscape where you had these channels that were driven by developmental trajectories. And so you'd start at the top, and he used this ball as the metaphor of unfolding development. And then development would unfold along these trajectories with these branching points. So you would have, and then the ball would represent like a phenotype. And then the ball would move down the channel to a branching point, and then the ball would either go down one trajectory or another, and it would keep doing that until it gets to the bottom of the landscape, which is supposedly the adult phenotype. And the idea is you could draw out these trajectories through this developmental space and define these different phenotypic possibilities at the end. So however that ball moves through these channels, that's sort of the developmental trajectory that leads to the adult phenotype. And one of the things about that landscape was that it was highly metaphoric, so it didn't really have a lot of detail. But actually, he did propose that, of course, this is all underlined by genetic interactions. So if you go back to the GWAS map, you see that there are a lot of contributing loci. They contribute at different amounts. So some are genes of large effect, some are genes of trivial effect. And then, of course, depending on your developmental state or your developmental period or phase, those genes contribute more or less. So this is kind of, and then he was very cagey. Well, not cagey, maybe he didn't have the detail in terms of the genetic map. So he just had these kind of these little squares and lines coming up. And it was, the idea is basically that was a stand-in for these genetic interactions. And so since that time, people have tried to quantify the map or quantify the epigenetic landscape. And so I think that can be interesting in the context here, which, proposes that there's, of course, a genotype that's being expressed. It's expressed into this developmental map, and then that developmental map leads to the phenotype. But it's basically generative in the sense that development sets up the adult phenotype. You can't just have a developmental process that leads to a phenotype, and there's like one combination of things that leads to that phenotype. There are all sorts of things like things like phenocopies, and you have buffered phenotypes. You also have pleiotropy, so you get different types of phenotypes from essentially the same genes, but the interactions are different, so they lead to different phenotypes. So there are different ways in which this phenotypic space looks that are totally dependent on the developmental interactions. So it's, again, an interesting set of concepts to play with. Now, this other paper that Morgan posted was also interesting. And so that talk is in that talk series that Morgan mentioned. This is Perspectives paper that is primary cilia as architects of the neocortex. So this again is a lot to do with brain development and microcephaly in this case instead of schizophrenia. Primary cilia as architects of the neocortex, roles in brain development, function, and microcephaly. So this is I guess a group out of Denmark and France. And they're looking at primary hereditary microcephaly, or MCPH, a condition closely linked to neocortical development. So initially, MCPH genes were thought to regulate a limited set of cellular processes, but recent studies reveal that many encode multifunctional proteins, often converging on primary cilia organelles that orchestrate the development of the most vertebrate tissues and organs. And so these mechanisms, these organelles that really kind of put together the brain in development. In this perspective article, we examine the role of primary cilia in brain development and explore how disruptions in MCPH and microcephaly associated proteins compromise ciliary dynamics and function. So these cilia are building sort of the tissue. The cells are being put together into this tissue in a certain order, and the cilia are working to sort of build that structure. And then the ciliary dynamics are affected by these genetic states. So the idea is that there's some disruption maybe in the genetic interactions or the genetic states in development, and it disrupts the way that the brain is developed into this adult phenotype. So they also want to explore how disruptions in MCPH and microcephaly associated proteins compromise ciliary dynamics and function. We highlight additional cilia-related proteins with potential influence on neurodevelopment. By elucidating the connections between primary cilia and neurodevelopment, we aim to provide insights into mechanisms of neuroregeneration. So it also has an important role in neuroregeneration, and they can understand that as well. Ultimately, advancing our understanding of primary cilia may help develop therapeutic strategies to restore neuronal function and improve outcomes for individuals with neurodevelopmental disorders. So this is focusing on microcephaly, which is something that it's a brain disorder defined by reduced brain size while maintaining an overall normal architecture. So it affects the growth of neocortex in terms of brain size. So micro is small and cephaly is head or brain. And then so the phenotype is manifest by an occipital frontal head circumference smaller than at least 2 or 3 standard deviations below the mean for age, gender, and ethnicity. The diagnosis of microcephaly is usually performed antennally during routine ultrasonographic examination or postpartum during the neonatal physical examination. Microcephaly can be caused by a number of genetic and environmental factors, including but not limited to in utero viral infections, teratogen exposure, which things like fetal alcohol syndrome, and metabolic conditions of the type listed here. Genetically conditioned primary microcephaly is termed microcephaly primary hereditary, or MCPH. So it's a specific type of microcephaly that we're interested in here, which is typically inherited in an autosomal recessive manner and primarily affects the development of the neocortex. Corticogenesis, the process of neocortical development, unfolds with the emergence of early neural stem cells, which expand in a number of in the ventricular zone of the cortex. So you get stem cells that expand in this ventricular zone. They migrate up and they form adult cells or differentiated cells. And so you get a limited pool of those neural stem cells, and you have less growth of the neocortex. You have a smaller growth of the neocortex, but you have the same architecture. It's just fewer cells. So you have neural stem cells, which give rise to intermediate progenitor cells that initially differentiate into neurons and then later glial cells. Subsequently, these neurons embark on radial migrational and glial fibers, reaching the cortical plate to establish dendrites and axonal connections, and culminating in the formation of this six-layered cytoarchitecture. And so the proliferation of neural stem cells influences the neuron count, which in turn shapes the size and function of the neocortex. So this is why you have smaller brain size overall. MCPH is genetically heterogeneous, with at least 30 genes listed so far in the online Mendelian Inheritance in Man, or OMIM, database, encoding proteins that orchestrate one or more of the patterning processes of the neocortex. In MCPH, gene variants affect primary cilia, which function as cellular antennae that orchestrate developmental processes in most vertebrate cell types. So cilia, they serve as these antennae in the cell. They kind of protrude from the cell, and they have this role of monitoring sort of the developmental process for the cell, so it kind of knows where to go, things like that. So this is a way to orchestrate developmental processes like neural stem cell pool expansion, axon guidance, and neural migration during corticogenesis. So it monitors sort of where the cell is in the brain, where the axon should go. These are all chemical signals, and then pool expansion, I guess, to make sure that there are enough neural stem cells in the neural stem cell pool, to know when to stop dividing, and having that sort of a self-regulating capability. These findings have contributed markedly to our understanding of brain development and cilia and neurodevelopmental disorders. So in this perspective article, we present an integrated overview of corticogenesis and the molecular genetics of this disorder, with a focus on how selected microencephaly-associated genes function at the level of primary cilium. We examine the multifunctional roles of MCPH genes within a ciliary framework, highlighting those most likely to act directly at the cilium. And then they explore ciliary mechanisms that influence both developmental and regenerative processes, emphasizing the emerging role of primary cilia and neural restoration. So they want to advance their understanding of how MCPH-related pathways shape brain development and may be harnessed to promote neural repair. So they're interested in this disorder, but they also want to know how some of these cilia play other roles in the brain, how these pathways also allow for plasticity, and so on and so forth. So there are a lot of aims in this paper, and they kind of go over what is known in the area. So this is a figure here. This is worth going over. I think this shows neocortical development. So again, you have this time course of cortical development in the human and then in the mouse. So when you see E, it's the mouse, E8, E10, E15, P1 through 3, and then P2 through 4. And then that corresponds with human stages WPC3, WPC5, 10, 22, and 25. So, they have these, basically they've worked out these developmental stages in each organism. And then there's an analogous stage in another organism. So since human and mice are both mammals, you have these stages that are conserved between the two species, and their timing is basically the same, but it's there's a different nomenclature involved. There's variation in the stages in terms of their timing, but they're all basically analogous. So this just shows the different types of cell. You have the cilia on the sort of the edge of the cell. You can see in this epidermal cell, we have motile cilia at the bottom. Sometimes cilia are sensory organs. Sometimes they help the cell move. There are different roles for different types of cilia. You have a primary cilium here coming out of the edge of the cell here. You can see you have different types of cells, neuroprogenitor cells, neurons, and interneurons. So you see the neuroprogenitor cell is sort of a precursor to a number of different cell types, and it differentiates accordingly. And of course, the cilia differentiate accordingly as well. You also have astrocytes, oligodendrocyte precursors, and oligodendrocytes. So you have neural precursors, which can become neurons. They can also become astrocytes and other types of cells. You also have these other things like oligodendrocyte precursors that have a more restricted set of fates. This is a radial migrating neuron and a tangentially migrating neuron. So you have different types of cells emerging at different stages of development. So in this case, we have these NECs that emerge very early, and then you have this ARGC, which emerges a little bit later. There's a pool expansion of these cells. So these are progenitor cells that form, and then they expand their pool size. So as you know, undifferentiated cells or precursor cells divide and then provide sort of constituents for neurons and other types of cells later. So we have this pool expansion of the precursor cells. We have then this differentiation process. We also get migration involving the cilia. So the cilia are basically picking up chemical signals within these different parts of the developing brain, telling the cell where to go, telling the cell where to project its axons, and so forth. And it's moving through the ventricular zone, the subventricular zone, and then into the different layers of cortex. Later on, you get this neuronal organization, and you get tangential migration so that different cells know how to connect to other differentiated cells. And you see the cilia are marked here to show that they're an integral part of this process. They're sensing their environment, and they're coordinating these kinds of migratory movements and organization into layers and things like that. All right, so that's basically development. This shows the dynamics of primary cilia and ARGC pool expansion. This just shows this primary cilium. It retracts a little bit here. It's basically being resorbed, and it's also then during cell division, it's being resorbed. The cell divides, and then you get these new cilia coming out. So you have ciliogenesis, which occurs in this part of the cell cycle. So you have a G1 to G0, or G1, G0, which is this where you have the primary cilium. You have the S phase where there's this resorption. You have the G2 phase where the cilia disappears. Then you get primary cell division or mitosis. And then of course, you get this ciliogenesis as G1, G0 proceeds. So the cilia retract and expand as part of the cell cycle. And so that's a kind of an important point when you're looking at these pools of progenitor cells. And these cilia are important for regulating the size of that pool. So if there's a defect in the cilia or a defect in how they are resorbed and generate, then you have reductions in the pool size. Or you could also have expansions of the pool size, and that could be a different disorder. So this is kind of just showing how these are genetically controlled, genetically mediated. So it's not like, we have these, I wouldn't say repeatable results, but we have this sort of tendency towards these things. Then we have in C, sensory primary cilia and radial migration of neurons. So this is the role of cilium in migrating neurons instead of regulating, say, pool size of progenitors. This is when they're moving to their positions in cortex and interacting with each other. So they're actually picking up signals from neighboring cells. They're guiding their axons. They're guiding their position in the cortex, and they're finding a place to settle, basically, and how to interact with their neighboring cells. And so this is where cilium are playing an important role in organizing that architecture. So interestingly, when you have defects in the cilium, you have defects in the pool size of the progenitors, but the architecture remains largely intact. So it's just a smaller cortical layer with essentially the same architecture. So, I don't know. I didn't, I haven't read the whole paper, but the cilia disorders have maybe a lesser effect on the organization of the architecture than they do on pool expansion dynamics. But yeah, that's basically what they're getting at here in the paper, and they go through a lot more detail in terms of specific loci and different mutations and things like that, and then just talking about how signaling pathways are coordinated by these cilia and how dysfunction can have profound consequences. And so this is a list of MCPH genes and their cellular function. So we know that they're involved. These loci are involved in different cellular processes, and so if we see that there's a mutation in one or more, we know that there's maybe some, maybe they have a function in common, and we can isolate those mutations to those specific functions. Okay, so that's a good paper. It's just kind of thinking about some of the things that are going on in the brain and some of these disorders. And it links back to that talk that Morgan posted before about a more general model of this stuff.
Sorry, I didn't realize my camera was on.
Okay.
Yeah. The really, really fascinating one, right? Because it gets. I love the infographics on those. I try to point out to people that, when I started grad school, it was mostly histology work around schizophrenia.
Yeah.
Right. And it was like post-mortem slices and things like that. And it was very, I don't know the best way to say it. It was very pre-internet in that there wasn't a lot of digitization. There wasn't a lot of they weren't thinking about biological scale the way that, to some degree, I think we've benefited from the internet scale.
Yeah.
Is that we're obviously talking about one of the most complex artifacts of the universe. and so often in this histological work, they would go in with a theory, which I could sort of get why, but they'd be something like, cell body size or connections or something like that. And this is again getting back to this lack of automation, lack of computer vision / computer intelligence.
Yeah.
This histological work was done manually, right? So, these poor grad students and postdocs that had to do this work, like understanding that this is painstaking, skilled labor.
Yeah.
Right? So to come away with histological analysis that shows that cell bodies of a particular cell type are smaller in schizophrenia versus controls, was like potentially somebody's like dissertation work,
Yeah.
right? And yet at the same time, right? Like so that would seem remarkable, and it would seem significant. The problem being that what time has shown is that basically anything you choose to go in and look at, there's differences.
Right. Yeah, there are always differences. It's just, what do they mean? You have to interpret them. Yeah.
So one, you don't understand the normative variability.
Right.
And two, it's just like, yeah, there are all these differences, but unless you actually looking for like 500,000 different metrics of connectivity, receptor type, receptor density, cell body size, every cell has like 1,000 features.
Yeah.
And there are 3,000 cell types.
Mm-hmm.
And in any particular area of tissue, there's some variable number of those cell types that are potentially ordered or disordered or connected together or not connected together. So you got this incredible variability across heterogeneity in terms of the cytoarchitecture.
Yeah.
And so when you see something like that, it's that paper, it's such a great testament to that. Just and on the one hand, they're kind of focused in on something because they're talking about primary cell.
Right.
But what I love about it is that it exposes the complexity in which that feature can be, like the many roles it plays, where it's coming from, what does it influence, all the other factors that come in development, and it's just the kind of thing where it's just like we need so much more data at such a finer kind of resolution, and all of it needs massive super scaled automation because humans can't take in all this,
Yeah.
And so it's the kind of thing where it's just this is why I think I love that the Soften team has gone from real-time effort. I mean, part of their commercialization is, yes, you know us from real-time fMRI, which is sexy but kind of useless. But we've got a startup, we've raised money, and we're doing medical reasoning training, and I think their clinical product will be medical reasoning and pathology. Right. Pathology as self-supervised computational histology,
Right.
right? And what I'm trying to get at there is like to link it back is just like, how do you make computer vision not just measuring cell size, but like literally taking in the whole visual input, right? And you know, so like on one hand you want a David Marr, you know, computational building blocks of like you know, you find the simplest geometries for everything, and you know, and you build up something. But like again, like these self-supervised techniques, like their internals are not that, right?
Yeah.
You know, and but what you are training, you're training them on tissue slices, right? So, but that being like, you know, we want eyes. We're fine tuning, or we're doing end to end training of eyes for tissue.
Yeah.
Right? Like they look at tissue and they see they can measure anything, and they can, you know, they can both see the complexity as well as take it apart.
Yeah.
And like yeah, like that will be yeah, that's what I want to learn from the Soften team, is like how to do that. You know, and I kind of like the fact that they're not 100%. They're not real. They're certainly not brain scientists, right?
Right.
You know, it's just like no. Like, let's not. You know, like our inclination is going to be like to have fully interpretable models at this point.
Yeah.
And like I think you gain from actually following the kind of tech path of make the end-to-end models do something.
Yeah.
And see what they've learned.
Yeah.
What, you know, like you'll get some achievements, and then like there'll be interesting things in the weights. You know.
Yeah. Well, that's good stuff. So I wanted to go over, before we go, a couple things from the chat. I know Jesse had an update, but like he couldn't speak on the.
Yeah.
So let's see. Sorry, I was in and out for a while. My only major update is a lot of JoPro work, continuing with Diginest in the year ahead. Also, data direction and data plus times direction and SET, which is Society, Tech, and Ethics and Technology. Discussion series in the works as well. Have a lot that needs to be published or put on YouTube. Yes, let's please get it. Let's get some progress on that. So yeah, thank you, Morgan, for the insights, and you know, maybe we'll follow up on some of this stuff. Again, we have the you know, the transcript available on this meeting, so we'll go through and look at that.
For sure, and yeah, I haven't forgotten about the things in computational psychiatry.
Yeah.
That would be like interesting to talk about next week. We're doing the new Tom Griffiths paper for reading group in next week.
Okay.
I don't. Anyway, I'll post it in the. Anyway, he's the computational cog sci lab.
Yeah.
At Princeton, and I think it would be interesting to look at that, as well as the LLM papers that for comp psychiatry that I talked about.
All right. All right. Thanks.
Okay.
See you later.
Take care.
Take care. Bye.
See ya.
See you. Bye.